and begin. I hope. Where's me? Yeah, and begin. Okay. It says I unlocked NAND score, so yeah. NOR gate costs 4 NAND, which, yeah. The only one I think I could improve was XOR. I've seen a few different ideas for this. For example, you do it with 4 NANDs like that, and the middle two go like that. So that's your 2 in and your 1 out for NAND, but that's not what I want to do. What I do want to do is put a NAND in there. I am looking at the truth tables at the top. I put a NAND in there and an OR in there. So that one's got an off there, that one's got an off there, and then we AND them together. Let's go that way. No, let's go like that. So when you AND them together, it's only when both of them are on do you get an ON. And that will be a NAND gate. It's got a NAND score of 6, which is the lowest possible, I think. And it also has a delay. It's got a delay score of 4, delay score of 2, delay score of 4. So that's a delay score of 8. Now if we go with NORs, there's a delay score of 6. Of course, a NAND has a delay of 2, so maybe if you did that, it's got a NAND score of 6. So let's go with a 4 NANDs, like I said I wasn't going to do. Yeah, NAND score of 4, probably delay score of 6. I get an achievement for that one as well. Yeah, if you can't see my pop-ups, I got an achievement for a 4 NAND XOR. This one's a little bit more difficult to explain the other ones because you have to see what that one's doing and why when you get to this point here it becomes an A and not B. But you've basically got a and a not A and not B in there. Or not A and B or whatever it is, and the A's on the second line kind of cancel out. It's, like I said, difficult to explain, but in any case at this end point here, yeah, at this end point here anyway, you basically got I think it's a not A or B and a and not B, and you flip it upside down when you go through there and you end up with not A and B or A and not B, which is your XOR. Anyway, that isn't really why I came in. Half adder could be done differently as well. you can reduce the NAND score by, instead of doing this for all three, you take it off this point, this point here with the bottom one, and then I think the top one's 1 and 2, so that would stay where it is. But then instead of doing these two where it's bottom one and that one, bottom one and that one, you take the XOR of it, because it's only on when one of them are lit up, so you end up doing both of them at the same time. So you could replace these two with one by going through there, but then that's got a delay score of 6. So the question is, do you want a fast one or do you want a cheap one? I'm going to stay with a fast one. It's not giving you the actual delay scores, but like I said, if you actually look at a component, they do have delay scores. It's not showing me on this level. This one, unsigned less, is a really complex one that I don't want to mess with. So we were where we left off last time. I'd just finished the leg architecture computer, which is this thing. Zoom out so you can see the whole thing. Slightly easier to program than, well, slightly, a lot easier to program than the other one, but it has drawbacks as well. For example, each instruction takes 4. Let's go back to, which level was it I was looking at? This one. Shift 1 left. So you have to implement shift left and shift right. But the programming code, I haven't actually added any things in yet. Add sub and or not XOR. We then go on ifs and jump test equal. So it's not equal to 0, it's equal, so just TEQ rather than TEQZ like we did on the previous computer. Then it's not equal, less than, oh no, it is that one, less than or equal. Let's go this one first because it's greater than, equal to, and then just greater than. And immediate 1, so if you put I1 and I2 in there, and the way you'd do it is, let's say you want an instruction. I haven't written the well, I don't, just an example here. Add plus I1, so that's that. Let me just merge it into one. Plus I1, add plus I1 will run the command for add and add I1 to it, and I1 means that this one here is an immediate 64, but then this one is addressing register 0. So add 64 to register 0, storing register 0. But what I'm more likely to want to do is something like that. Add 1 to register 0 and storing 0. I usually, this is a command that I would use somewhere that basically just means increment whatever's in 0. So you load from 0, store back in 0, and add 1 to it. So we actually want to let me load the leg if, because I looked at this as well and realised it's wrong. I mean, it's not wrong, it's just wrong. It's not actually wrong, it's just not what I want to do, because I added a second one here for a greater than, but in theory you don't need that. Because I want to move this. Let's just cut all this. I'm gonna have to load back to level. So our instructions are, just take this in a notepad to make sure I wire it up the same way around again. So it's equal, not equal, less than or equal to, then it'll be greater than, then greater than or equal to, yeah, greater than or equal to. Right, so I'm not sure if I did that on stream or afterwards where I programmed the instructions, but if we go back into the leg if, so what we can do now, where's my mouse pointer gone? There we are. What we can do now is lower these, which gives us more room for other stuff up there, which we don't actually need right now. Like that. Take these off. Probably go that way, like that. There you go. Usually a bit more going down there. Microphone definitely is working. I want to put OBS on this other screen like that. Right. So equal to not equal to, less than, put this up here a bit, oh no, there we go, less than, and we'll put our less than, whoops, and equal to here, so less than or equal to. What is a greater than? A greater than is the opposite. Put these not gates here. A greater than is the opposite of less than or equal to. And likewise, greater than or equal to is the opposite of a less than. So if you put those like that, you've done everything. Now Yeah, I put it there, but it's... I'll need to get rid of that one first and then reroute it afterwards. So where was that? Less than there. And how far can I push this? Oh, I'll probably push it about there. It's still not quite far enough. Let's leave it there for the moment. I grab this lot and push left and push left. Oh, almost there. Grab the whole lot. Or no. Yeah, I think I'm gonna... It's ugly like that, but it's this R that's in the way. If I lower... No, I can't really lower that one. If I lower everything up there, it's a mess now. Oh, but it actually worked. I'm just trying to get the shape. Yeah. So back to level. And we will have disconnected this here, but that's no problem. Because I want to go like that. Right. So the next thing is we'll load up the ALU. I want to squeeze all of these as far left as I can, which can go up one, down one, whoops. I want one of these just go like that, so whoops, so I can bring that up there. Bring this like that. I can bring the adder across like that. Aha, there you go. No. Clear. Yeah. If I then grab, let's put that there, a little bit more space, everything across a little bit. Oh look, my ALU can be smaller. Don't want to actually go smaller though, because I'm adding stuff. I now want 2 of those there. with switch there and there. Let's lower this again. There. Don't want to miss though. And probably go with a yellow like that. So like not, it's only the first instruction here that actually does anything. And so what's shift left? Shift left is connecting one higher, like that. And shift right is connecting one lower, like this. So shift left and shift right. Can't go. It really does. If I move that down one like that, now it just wants to go over it. You know, it doesn't matter. So that should be our upgraded leg ALU. So we need to define instructions ALU. Ah, yeah, that one. Define instructions. New instruction. It's. Is it this bit? No, it's not this bit. It's that bit red with that rule is shift left. I'm just thinking this out. Yeah, let's just go with its suggestion, shift left and shift right. So it says to shift left, yeah. The task in this level is to shift the first input to the left and then output. Then shift the next output to the right and left again and so on. It's strongly recommended that you add left shift and right shift values to your hardware instructions. Yeah, which I did. Don't know if it's going to be useful in other levels because anyway, you can accomplish a left shift by adding a number to itself because it's just multiplied by 2. The most significant bit is then chopped off. Right shift is divide by 2. So it's not so easy to do in software without the hardware we just added. So it's shift left then shift right. So shift left in the matter and out, shift right in doesn't matter, out. No, I think I saw in the intro, you know, the Steam demo video that tells you about the game, that you can put the underscore in there. I'm guessing that they just defined underscore as 0. So we added shift left and shift right. We also probably want to store the numbers reg 0, reg 1, 2, 3, 4, 5, 6 is program counter, so let's just go PC for program counter, and then in, but also out. That simplifies our programming a bit, because instead of having to remember all the numbers, we can just, for example, go like that. But we're putting in 0 because we don't actually want 1, so let's just add that as a 0 because it doesn't matter. And that should, in theory, be our program for this level. It seems to think so. Delay, yeah, I should have done this first. All components have a delay, and in a circuit the total delay is determined by the slowest path. This means you normally want to put things in parallel. In this level you must prove that you understand this concept. Delay of any component is ultimately derived from the delay of the NAND gate, which is a delay of 2. Build a circuit with a delay of 6 and an AND cost of 5, and is going to give us 1 input. I'm not sure. I mean, the circuit's going to be nonsense anyway. Because it only give us 1 input. We can now view the delay of circuits and components. NAND delay, tick sum. Yeah. Got NAND delay and sum on all these levels. Now an interesting question is our XOR gate, we've done that. It's got a delay score of 6. Does that mean our XOR gate in later levels, like we come back up here, our XOR gate has a delay of 6? Yeah. But does that extend to something like this? A delay of 12 on our full adder and an AND score of 20. 12 and 20. Adder 12 and 20. So yeah, it seems that whatever circuit we design influences, you know, the actual component we get to use later on. So while they're not custom components, Oh, sorry, I just looked around and noticed that someone's been sending me messages in the chat. He's just basically saying, I love your Factorio mods. Probably gone. It's not saying anybody's watching me at the moment. Either way, thanks. So we can either make, well, we've made RAM, so we can either add, let's do something with RAM, probably add it to the circuit, because he did mention it in this last step here, or product of nibbles. Multiplying two 4-bit numbers gives you an 8-bit number. Build a circuit that does this. The obvious way is, if you want to multiply, you add however many times of one by the other. But we don't want to do that exactly. I have already looked up circuits for things like multiply and divide, just in case they'd come up. So if I just go OBS, if I click on screen, that is something that I found that it basically does what we want. So I'd have to translate this thing, which it does try and explain how it works here, and to some extent I have gone through and figured out that yes, it seems to work. Because, for example, 1 times 1, well, this bit here is bit 0 of y, which is one of your inputs, and bit 0 of the other one, ANDed together, which means they both have to be 1 to get a 1 out, goes to z0, which is bit 0 of your output. So 1 times 1, well, it's just 1 and 1, and you get 1. So that makes sense. And then what if, for example, it's 2 times 1? Well, y1 is the second bit, the second bit of one of them. So 2 times 1, well, 2 times 1, oh look, we turn on bit 1. It don't matter what this one is, because and then this is y0 and x1. So if you flip them around so that this one's 2, and so that y is 1 and x is 2, well, that goes to the same place. And this adds, if there are both a 1, well, that would be 3 times 3, which is 9. So this one would turn on, but then this one would turn on, and this one would turn on, and that would actually give you a 0 and carry, and that carries through here, which would turn it on, because we're ignoring everything above that so far. So when you understand what you're trying to do by multiplying in binary, the circuit makes sense. It's kind of like a pattern. So let me switch back to Turing Complete and put this back on the other screen like this, which means I can't see. There we go, now I can see. Which means we want this somewhere right down in the corner with that next to it like that. As much space as possible. I'm gonna rotate that one. So this is our 0, and this is our 0, and this is our 0, this is our 0, so 0, 0's here. What I'm gonna do is not too far, something like that. It's not centered anyway, so let's just go straight down. Like that. Out one, like that. And across, and that's the wrong one because that one wants to go across. That one across there, and there. Trying to make them fairly even, and then it was where I wanted to put it, just yeah. Okay, so the first one we're using the AND gates, so we'll put one there like that, and there's an AND gate at every intersection, so at every intersection we want to add an AND gate, which basically gives us the 4x4 array. Don't miss. Get rid of these as well once I've connected that to it. So the first one is, this is 0 and 0. Can I add text? Let's call this x0. This, keep that on. This is y0. Turns off each time. Y1, Y2, Y3, X1, X2 and X3. So that one goes to there. I'm just looking at the you know, the thing. Then take x1, y0 and x0, y1 to an adder, and this is a half adder, so the carry's not used. There's a few of them where the carry's not used, so what's that one? Y2 so y1, I think I've labelled these backwards. Just remember x's are y's, so then it's y2 x0 like that. I think it's a 4x3 grid. Anyway, that one went to there, I think, like that. So x0 y1 and y0 x1 go to the same one. So y0 x2 is y0 x2 y0 x2 with y1 x1. Yeah. And then y0 x3 with y1 x2. Yeah. So yeah. Now we add another adder. Is it here? Does that want to go to there? Y1 x1 maybe not. Y1 x3 or y1 x3. I think I'm getting the numbers confused as well because I labelled it backwards. So what have I placed? I've placed x0 y, yeah, x0 y2, yeah, goes to, so this first one first, x1 y0 output goes to here. Its carry goes to y1 x1 there. So the other way, y1 x1, which is the same no matter which way around you look at it. And the output of y1 x1 y1 x1 goes into another half adder getting confusing. That one goes there, and then I think it's this one. So what is... See, I'm getting confused with that's doing there, but it doesn't actually go there. Y0 x2, so x0 y2, x0 y2 goes to z2, so that's here, and the other inputs connected to it are x2 y0 x2 y0, and that makes sense because that one went up there like that, and instead of going across there, is it this one's carry or this one's output? It's got one feeding into it that goes to, it has x1 y1, which is here, so that goes up there, and x0 y2, so yeah, this one's output goes there. I'm going to get past all the head fragging. So pattern suggests that this would go here. So this is x0 y2 x0 y2, which also has x1 y1 going into it, which is true. Why am I looking at this? Oh yeah, because the carry goes into the one intersecting x1 y2. Well, I don't know because I haven't connected anything to it. x1 y2 x1 y2 to solve confusion. X Y Y Right. So this one I think wants to go up to here. So the question is that right? So this is from x0 y3 x0 y3 think I've just confused myself even more by renaming them. I see a pattern anyway. Let's follow the pattern. So this one goes down like that. This comes up and back. That's the one down there. Yeah, I need 12 in total, so there, and there. This one's gonna go there, 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 and there. And we're gonna go there. That's gonna come down. This always goes up and left, I think. Does it? Where's this one go? Down and right, like that. Which means this one goes there. Like that. I think. No. I've done something wrong. We have a carry here that should probably be connected to something. So try that. No. Oh yeah, we have a carry here that's now not connected to anything. We also don't have anything on the highest bit, so according to the thing, yeah, carry from the corner one goes to the bottom. This one doesn't have a carry. So carry out. What about this pin should probably connect it to something, and this pin. Oh no. There's 4 of them that don't have a carry in. 1, 2, 3. 1, 2, 3, which means I'm missing one because there's 1, 2, 3, 4, 5 that only have. Oh, yeah. So I'm missing a pin somewhere. Well, I haven't tried it, so let's just see if it works. No, it doesn't. So I guess the pattern system didn't quite see. That's got a carry out that's not connected to anything. Maybe if I connect it up like that. That was what was missing. So what you did here was actually multiplying two 4-bit numbers. We had the intern scale it up to bytes instead, so the result is 2 bytes. Unlock a 2-in 2-out multiplier. Divide. Integer divide. It's given as it on our thing, so we're writing a program. Integer divide two numbers to find the quotient and the remainder. Something this. It's given us a screen as well. Integer divide two numbers to find a quotient and remainder. Consider the fraction 7/3. 3 goes into 7 2 times and 1 is left over. 2 is the quotient and 1 is the remainder. In this exercise you are given the numerator 7 and the denominator 3, and you are then expected to output quotient and remainder. So we want to read in, add, copy is just add where you take a value and add 0 to it. So let's put it in the quotient, the numerator. Yeah, numerator. Add I2 in not reg 1 denominator so we want to then do is greater than or equal to is reg 0 greater than or equal to reg 1, and if it is it less than, go to output. If it's not less than, what we want to do is subtract from the numerator the denominator. Why is sub? There you go. Subtract the denominator from the numerator. Let's just save over it. Then add register 2 1 reg 2, so that's the increment reg 2 command. remainder. No, not remainder. Quotient. Then go to. I haven't implemented a go to yet. Go to check. So to do a go to, we don't actually have, like the previous one, the comparison for always. So that is something we might need to do at some point. What we can do is add I1, I2, add that's a go-to. We take the value of an address, add 0 to it, and store it to the program counter. That's a go-to. This is also a go-to. If 0 is equal to 0, then you go to thingy. So we have a few ways of doing a go-to. Stick with that one because it's a bit easy, a bit simpler. Go-to. Okay, so that should loop, and is that right though, this check? Because if reg 1 yeah, if that's less than that, we want to do this. No, if that's less than that, we're done. Yeah, that's right. Add reg 0, no, quotient first, reg 2 0 out, add reg 0 0 out. So this should be our quotient and this should be remainder. That should be our program. Oh, I didn't mean to press play. We found an error. 251 divided by 36 should be 6 remainder 5, but for some reason we have 216. Right, 251 36. So we go through add. Oh, we haven't put our I2 in there. Add 1 to it, yeah. So then we go again, subtract 36 from it, add 1 to the quotient, subtract, add, test, subtract, add, 71, 35, so we have 6, we should go up there, jump down, so output our 6 and then 35, so yeah. Large number divided by small number. Let me close this picture of the multiplier. Okay, so we have the sandbox and the lab, which I don't think I want to go into, at least not now. RAM. Add a RAM block so that the computer can address 256 additional bytes of memory. You need a way to decide which of the 256 bytes inside the RAM we are addressing. Select a register and wire it up so its value always detects the RAM address. When you later want to load or save to the RAM, you will have to first copy the RAM address to this register. Select a register and wire it up so its value always selects the RAM address. Basically what that's saying is if we want to address RAM, first we have to write a value into, let's say, register 0, and then register 0 is basically RAM address. Memory. That's one way of doing it. That is how Overture basically worked. We had a register that did something specific. So if we say that's the RAM address, in this test, first copy from the input 32 times and store these values. After you have loaded all 32 values, output them in the same order as you got them. So do I actually want to do what it is telling me here? Do I want to select a register and use that as the RAM address? According to the information at the bottom of the screen here, we have a load, save, address and save value and output. So load activates that, save activates that, and the address is used in both modes. Like a single one here, you got load and save, or two loads in my case and a save, an input and an output. So I could, for example, do that But then what goes on there? If I did that, I'd basically address RAM as if it was. I'd disconnect this. But yeah, what it's telling me to do gives it two instructions. First, you put the RAM address in, say, here. Then what? Huh. Yeah, I'm just thinking, seeing, just thought process. So you save to that address. So what do you connect to here? If, for example, we connected that to there, well, then you'd need a way to address this. But if this register's holding the address, you'd have to sacrifice another one another register is the load and save. So these would connect up to there, and that's to the address. If you're putting the address in a register, then every time you want to load or save to RAM, you first have to do that, then access the RAM. What if let me move this down 1, 2, yeah, down to here. Then have these let's just go from there to there. Let's do a gap of 3 like that. There we go. Then we want to go. Let's go out a bit. Put this on magenta. Okay, rotate that like that. I put this further over here now. Look, in fact, I could probably put it there, and I severed something. This, by the looks of it. Now, if I remember correctly, the top ones, yeah, that one. The top ones go there, so this one's the top one, and this one's the second one. Maybe it wasn't such a good idea to put that there. No, nonetheless, it's connected. So then I need to figure out what is the load command and what's the save command. The way I have this wired up, address goes, argument 1 is address, argument 2 is data in. So if you're saving to RAM, argument 1 holds the address, and as it's wired up, I could put the address into one of these, and then if I want to give an address specifically to the RAM, I use immediate. If I don't, use a register. So that could hold the RAM address, and that could hold the RAM data. Put it in. Yeah. As for this thing, load and save like that. You need a custom component. New custom component. New component. It's our RAM controller, RamCon. So we want byte in, one bit out, and then we need to define an instruction. So these 3 are used for instructions. These 2 are for immediate, and this one is, are we doing maths or are we doing a decision? Now in theory, if we did replace a register, then we could load from RAM out by addressing it using the yeah, this will need a lot further thought, because this is coming up with the architecture without the game telling you exactly what to do. So for the time being, let's just say if this bit is on, let's put an and. If this bit is on, we're addressing the RAM. So I don't care what this one is, because we're overwriting the instruction. Think of these two bits as choosing what we're doing. If this is a 0 and that's a 0, we're doing maths. If that's a 0, that's a 1, we're doing a decision. But if that's a 1 and we don't care what that is, then we're addressing the RAM. And keeping it simple, we'll have it was load first and save second. And this is opcode. Want to not get if it's a 0, if it's I don't know the way around. If it's a 0, we're loading. I think. Do I want it that way around? The other way around. I'll probably change my mind later. If it's a 1, we're loading. If it's a 0, we're saving. So now let's put our ramcon custom component there. I don't like the shape of it. Now the wiring's just a mess. Okay. There. So we need to go into here and change this so that it is specifically zero zero. So if we get an OR gate, can we move this further to the right? If we had a OR gate like that, and if either of those come on, we disable it. And this thing we specifically want that off and that on. Let's do the same. Like, still on the grid, still on the grid. Okay. Can we fit it in? We could barely fit it in there. We need this one to the right, so let's just go let's go everything one to the right, then this one to the left, and then all of this, yeah, one to the left. One to the left. So now there's extra room in here to fit that. Like that. So not 32 should still go in to disable it, and if this comes on it disables it. So that should disable our leg if. Now let's just load up this one and simulate it to see if things still work. And this one, things still work. So we haven't broken anything. Right. So load is when it's on. So we need to go back into instructions, define ALU like that, if like that. So I'll have to go and do this with all our if and math functions like that. Yep. Then a new function, off, on, RAM, and when it's off and on, this was save, and this is load. Save, load. And that's what we want to do. So if we go back into the program, call it RAM S and RAM L. So RAMs reg 0 in, so it's address first, then data, and we don't care because we're saving RAM. Then we want to add one to reg 0 and store back in reg 0. We then want to check if reg 0 is equal to 32, so add I2 to it, and if it is one less than, because if it's not 32 we want to go to start. If it is 32, we want to go add I1 I2 0 0 reg 0. Well, I'll put 0 in reg 0. That's how we're resetting the address. RAML reg 0 for our address. We don't care because we're loading. I want to put it in out, and then it's just copy that, label output. Let's just copy this. If it's less than 32, go to output. But really all we need is an actual go to output, because it resets the program every time every time it finishes its sequence. Besides, I think the mission ends. We'll do it 3 times, but I could add a go to start, which is tech 0 0 start. We don't even really need to put I1 I2 in there because it's just comparing register 0 to register 0, which will always be the same. So, and we want to add that. Watch list RAM. Address 1, value 0. Add 1, value 216. Yeah, 165, I think. 166. It's not working because it's just wise. Why does reg 0 keep resetting back to 0? That it's because our hardware is incomplete. We're still addressing 0 during the RAML and RAMless. This needs a disable adding in when that's lit up. We need more space. We can easily make space by shifting that left. So that no longer wants to connect directly to that. We want OR gate, put one here and one here. That. So yes, we want that to there and that to there, but then that goes there, I think. So let's run it through again. 1, 0, 1, it's still resetting. RAMs is still turning on. Oh no, it's turning on the. It's turning on the disable. Let's tick through. Why is it resetting to 0? I'd want reg 0. Test if reg 0 is equal to 32 or less than 32. If it is, you go to start. I'm not even reading ins. I'm not sure what's going on here. I know what's going on here because I just did that with this. It's more complex than I thought, isn't it? Yeah, we don't want that. We want to address it to load, but not the destination. But we do want the destination here. So get rid of these. Put that back up there. So we don't care what goes on here on the load. The one that we need to not do is we need to not use destination specifically on RAM load. So we need an OR, we need an AND gate here. So we need an OR gate first, so that we separate this, and that's one of our things. But the other one is, I'll have to wire that up again in a minute. The other one is this, and RAM S, not gate, there. So then this goes on there, and this goes up there. So we need to not do this when that instruction. Nah. Try that again. 1. Yeah, we saved it. 2. Ah, yeah, we're actually counting. It gets complicated fast. If we go up for a branch to do some interesting, I could continue. In order to cut spending, it has been decided to change the queuing system at public offices so that fewer people will go. Instead of first come first served, we are implementing a last come first served policy. Think of it as like a stack of numbered slips where the citizens either put a slip on top called push, or the bureaucrats take one off the top of the stack called pop. When we want to implement, we want you to implement this new system. Each tick, the input will either signal push or pop. If it is push, store the value on top of the stack. If it is pop, remove that value from the stack and output it. So we can move shit. RAM. Still got a funky colour. Make space. Each tick, the inputs will either signal push or pop. If it is push, store the value. When it is pop, remove the value and output it. So store the value. So we need an address, which means we want a register. Let's turn these on. We want to either add one or subtract one So you need an adder. Probably want to put it there, like that. Constant set to 1. Maybe. Input. Pop. Push. Push is save. I want to save anyway, no matter what we do. We want to load anyway. So you always want to load and save. Pop is a load. Push is a save. So we want to add one. We want to add one and we want to can I type in negative ones, just all of them? Something's not quite right. So it's incrementing fine, but when we want to pop, oh, let me move it left to make room, because I think we want to have a pair of switches here. And that one on save, that one on load. Connect it like that. Pop, push, pop, 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 Yeah. Oh. Because the way the memory works is, I read somewhere, can't remember what, the way the memory works is there's normally we can't see the clock signal. When the clock signal goes rising edge, so transitions between 0 and 1, it performs a load save action. And then when it goes from 1 to 0 on the falling edge, it performs the other action. So there's a delay between loading and saving. We unlocked the stack. Push and pop. In this level, you are supposed to add the stack to your computer. When it is 0, you should pop a value off the stack. When the input is 0, I should pop and output it. When the input is not 0, you should push it on the stack. So first things first, add a stack. This is data. So if we do it like RAM, we have that. Pop, push, load, save. Pop is a load. So we don't need an address, just data. I'm going to go into ramcon and modify this so that we have an AND gate here, the NOT gate, I don't want magenta, like that. So RAM only works specifically when that byte is not. I want to go back in because I want to clone this. What's this one? Rename. StackCon. Right, and our StackCon pop, push, so push is 0, add a NOT gate there, I think. Do we? No. That way. It's only when they're both on. Yeah. Right. Stack con. I think on this one I do actually want it there. Like that. So what does that make pop? Pop and push. Pop is the top one. It pops when 1. So now we're back on RAM. It pops when 1. So we want to add stack. Push. Pop. Like that. Why is the RAM using a stack con? Where's my RAM con gone? There is a RAM con. It's there, look. RAM con. Yeah. Why is that now saying RAM con? Where's stack con gone? Switch schematics, RAM con, stack con. Well, I want a stack con there, not on the RAM. There's stack con. Where's my RAM con? This is crazy. Component factory, stack con, switch schematic, RAM con, switch duo, return to level, con. Huh. I have no idea what's going on, but it's not behaving properly. Ramcon, return to level. Now I have seen copy paste work sometimes, but not others. And this is one where it's not. In any case, Ramcon delete stackcon Ramcon opponent foundry, switch to something new. Ramcon's still there, everything else is still there. Got a blank one. Component factory. Stackcon. Stackcon, it's there, look. I'm not going to try and add it to the circuit while it's blank though. Okay, ALUs. We want byte input, 1-bit output, there and there. Pop, push, opcode, and this thing with, what was it? I forgot now. An AND gate here and here, an AND gate like that with a 1 like that. Yeah. Stackcon. Hey! Stackcon and Ramcon. Right. Is it that simple? So I want to write a program. And we're in RAM. Well, while we're in RAM, let's make sure everything still works. Seems to be working. And divide Make sure program still works in here. Seems to be. These two look. Oh, this one seems like a good one for checking the general. These two, because I use them a bit in it. Right. So, if I'm gonna need to add push and pop as new instructions. So add I2 in 0 reg 0 check test equal reg 0 0 and do pop pop don't care out otherwise push don't care reg 0 don't care go to is not going to label it, but that's push and that's pop. This is go to, yeah, if there's 0 do pop, otherwise do push. Okay, so 18 should push. I should also add the stack. There we are, stack to the watch list. Yeah, I can see it there. Zoom in a bit so that it's easier to read, like that. So we've put 18 on the stack. Our next value is 245, so we want to add that to the stack. Next value is 0, so we want to pop. Yeah, do pop, popped out, push. What? You did not pop and send your last value to output. Push. Huh? Pop. 117. Push it. It's complaining you did not pop. It didn't want me to pop. It's not a 0. When the input is 0, you should pop. When the input is not 0, you should push, which is what I've been doing. So why is that failing? Pop value 0 off the stack. Well, you should never return a 0 anyway. Add the stack to your computer, yeah. Push 117. Add the stack to your computer. What's it complaining about? I don't understand why it's not working. I've successfully pushed and I've successfully popped, and then it's complaining that I didn't pop 0. Why would it want me to pop 0 anyway? It's push on the star. Yeah. Pop value 0 off the stack. So it's giving me a 0 and then it's complaining that I'm not popping. But it hasn't given me a chance to pop yet. So 117, it's a non-zero. In is 0, so I want to pop, yeah, 117, you did not pop and send the last value to output. Well, the last value was 117, so we're not supposed to pop. Reading the 0. Reading 117. I don't see this lighting up. Alright, so from the beginning, we read in 18, we read in 245, we read in 0, pop. This should be popping and addressing output, but it's not. So in this state, this is disabled because this is on. What's this one? Oh god. That's the problem. This needs rewiring so it comes on specifically when this is on and this is off. So when this is on, and what's this one? Yeah. Do it from the bottom up, like that. I need to do a little controller for this thing at some point, get all this logic built into it, like I'm doing with the RAM and stack controllers. Right, so let's lift it up, put it here so I can see what's going on here and here. So we stored 17 from the beginning. We store 18. We store 245. Then we're reading a 0, which goes to do pop, and pop turns this on and outputs the value. Then we're reading 117. Then we pop it. Then we're reading 35 and store that. And it's going, it's working. Since we rewired things, let's double check divide. Stop, run at 100. There we go. And RAM. I might as well check. Oh no, we can't check stack because that's what we just implemented, the stack. Sometimes it is useful to reuse a section of code. We call these functions. To implement this reuse, one can jump to the beginning of a function and jump back again at the end of the function. We call jumping to a function calling, and jumping back from the function returning. But for this section of code to actually be reusable, the return jump will have to be able to return to different locations depending on where we called the function from. We want to save our counter value to a register before jumping. We want to save the counter value to a register before jumping to the function and use this value when returning. However, if done this way, a function will not be able to call another function since this would overwrite the original return address. Say function A calls function B who calls function C. When we want to return from C, we only need the return address for B. And in B, we only need the return address for A. In general, regardless of which function we look at and how they are nested, the last return address we added is always the first one that we need again. This is exactly the behavior of the stack. In this level, you are tasked with implementing function calls and returns with call and ret instructions. Well, in theory, ret's already possible because we just pop the stack to the program counter, which would be pop blank blank counter, or PC I think it is. So we've got a return call. Note that when returning from a function, you should jump to the address that comes after the call instruction, otherwise you will end up with an infinite loop. The call instruction has to do the following. Call instruction, add the instruction width, as 4, to the counter value and push it to the stack. Then jump to the function address. Is he going to get more spaghetti up there in the address controller, I think. Return is easy because you just pop the return address to the stack and jump to it. So pop is, as I said, return is just pop blank blank program counter. Pops the stack to the program counter. What's this? Level is complete. Oh, there we go. Budget cuts have led to cutting salaries, but now the lab assistants are on strike. You will have to self-assess in this test. This will tell us something about your honesty. So how do we do a call? Call needs a destination. So the instruction would be call something, possibly blank. Call program counter. No, call blank program counter plus 4. And push this one to the stack. So that's in there already. Push this to the stack, which means you want to turn on this line when we have a push instruction. A call instruction. So let's just push. We're not popping, we're pushing. So start with a copy of push, but we're doing call. This bit's determining read write, so that's call. which means we want to add call. Did that add to the list? Call. So I want to go into stack con. I want to add I want a switch in here. We don't have switch duo. What we want is we want byte output to stack data byte input data in program counter in. We want fairly close switch no, that's destination. What was program counter? That colour, and I think it was green. And let's just keep it simple, put a not gate. Put a not gate here when this bit like that. No. That, so when it's off, this goes through, but when it's on, this goes through. Oh, and we also want this. I want a 3 input AND. This, and not this. Pop. No, we're pushing, aren't we? No. I mean, yeah, we're pushing, but that is a not. That is a not. When we're pushing. And put it in this cell. This is PC enable. Yeah. And the program counter, yeah. Why is it ugly? Why has it got that bit there? What's causing that? Is that our NOT gate? That's our NOT gate. So if we pull this left a bit, like that, You don't need to be that big, but at least it's not got that ugly. So if this, I want to do that, or if this, and yes, we want to turn that on. So this line here wants to come on if that or if that. So we want or gate if that or if that, do that. There, tidy. But we don't want to just do that. We want to do, where's math? Add. That's it. Add four. So stack plus 4 gets pushed. And everything else, I think, remains the same. This, don't matter if that's on or off, because so this one specifically turns on to disable the addresser when we're using the if. This one disables the addresser when we're doing a load. Since pop is a since push and call are both save, nothing changed from previous. Right. What level are we in? We're in RAM again. Why are we in RAM? Well, it gives us an opportunity to make sure we didn't break it. Likewise, let's go back to divide and make sure we didn't break it. So we want to be here in functions. So I've implemented it. I could just do that, but label start, call func B, label func A, label func B, call func A, return is pop 6, no, PC, which is 6, pop PC, go to end, label end. So go to is add, no it's not, go to is, yeah, tech end, tech start. So what we should see is that we start here, then we go down to here, then we go up to here, then we'll pop back to here, then we'll pop back to here, which jumps us to here and back to the start. So it's just jumping all over the place and not actually accomplishing anything. But that should test. Right, so call. Counter's already saying 12, which is here, and 4's on the stack. Call funky. So counter says 8, we've got 16 on there. Pop PC, let's put 16 on the stack. And then that's put 4 on the stack. So now we should end up here on line 3, which put 20 on the stack, which is down here, which put 0 on the stack. So that's a call. So we've got 2 calls, 2 returns and 2 go-tos. Yeah. So call and return works. I suppose in theory I could hardwire in a return, so it's just don't care, so it's just return don't care, don't care, don't care, and then add some circuitry that activates a push and turns this on. But that'd need to be one that doesn't activate this line. That'd need to act, yeah. So, is it complete? Yeah. And he believed us. And I've been streaming for more than 2.5 hours now, so there. I don't know if or when I will stream this again, but if I do, I'll probably have a plan on how to make the computer better. I think everything, yeah, assembly challenges, I think everything beyond this point is some sort of, you know, challenge for you to just program something on your computer. So yeah, leave it there for today. The game crashed while trying to exit.